All right, so we went ahead and we looked at friction, and there's a couple different types of friction. So we know our two general types of friction. The one that's currently affecting you sitting in your chair right now because you're at rest is what type? Starts with an S. Static friction, right? I am currently moving around the room, and so between my feet and the ground, because I'm in motion, what type of friction do I experience? Kinetic, right? Now there's another type of friction that I'm experiencing as I'm walking through the room. It's not very much, but if it was a really windy day, you could see my luscious locks flowing in the air, right? What type of friction would that be? Air resistance, right? So we had originally said that air resistance is a type of friction. And the reason it is a type of friction is because it actually opposes our motion, okay? So anything that is going to oppose the motion is going to be classified as friction. I know on our actual diagrams, we diagram it as something else. We would actually classify it as F air, but both are a type of friction, okay? All right, so as you were going down the track, so the very, very first page was all your setup, everything like that. Once you rolled it down the track, what did you notice about your speed here? So in the first data chart, was your speed pretty consistent each trial? And it should have been, right? It should have been fairly consistent. So then when you got your average, can somebody give me approximately what was your average for your speed? I know y'all are looking at it. Anna, what do you got? All right, so centimeters per second, right? All right, so we were going about 115 centimeters per second. And so when we were looking at that, we're like, okay, well, I'm covering a decent amount of distance. Remember, it's not meters per second. A lot of people are like, well, that number's really big. Remember, it's centimeters, okay? Then all of a sudden we added this sail. And so when we added this sail, this caused for more air. If you have a greater surface area, it's going to hit it, right? If we neglect air resistance and things are falling through the air, everything accelerates at 9.8. So if I take two objects, even if they're of different masses, they're going to hit at the same time, okay? So if I negate air resistance, everything should accelerate down to the earth 9.8. But if I do have air resistance, is it going to accelerate that fast, or is it going to be a little less? It's going to be a little bit less, right? So hopefully with your hypothesis that you filled in here, hopefully you made an estimation whether you thought the speed is going to be more, less, or the same, okay? Now, knowing that the air resistance, if my car is moving to the right, we know friction is going to be acting to the left, okay? Or if you're falling through air, your motion is down, but air resistance would be up, okay? So it's always going to be opposite. So then when you take a look, Anna, on your next, your average here. 106. All right, so overall, our actual speed decreased, okay? It wasn't able to accelerate as quickly because it experienced more air resistance. Now, some of you guys might have been better MacGyvers and taped it on pretty well, and so you saw a greater decrease, or maybe your sail was kind of a little floppy and it maybe didn't affect it as much, but we should have at least seen a change here, where the average speed was a little less. And that's as to be expected, okay? So that is as to be expected. Our last two types of friction that we looked at were sliding and rolling friction, okay? Now the nice thing, if I am taking a box and I'm deciding I'm gonna move a different place. If I just try to push that box along the ground, remember that has a big surface area. The bottom of the box is touching the ground, so it's going to be harder for me to push that. So what do a lot of movers use to help them move things that are heavy or things that are big with big surface areas? What do they put under the couches or put under the boxes? You guys know what it's called? Looks kind of like this. Anybody know what that's called? A dolly? You guys heard that word before? A dolly? Okay. So with the dolly, or they also have these things that are just a flat, it almost looks like pieces of wood. And then on the bottom, there's wheels. So then they can set like a couch on it. So in that way, they don't have to hold the couch the entire time. That way they can do less work. Next unit we're going to talk about is work. And if I want to be able to do work, it requires a lot of energy. Well, if I'm going to do work, it requires energy. That must mean I'm exerting forces. So as I'm looking at that box and I'm like, okay, well, I want to get it to move. If I put it on wheels, is it easier or harder for me to move? Easier, because there's less friction, right? So when we were comparing these two, hopefully you had this response, that my sliding friction caused a greater negative acceleration because my sliding car had a greater surface area in contact with the ramp. So it's going to slow it down even more. Whereas with the wheels and the rolling friction, I shouldn't have saw as much of an acceleration in which it's a negative acceleration was slowing down. Okay. So did your guys' results agree with that? Look at table 3. Your average, was that a greater negative than your average from your rolling friction? Good. So I'm seeing a lot of nods. A lot of people are like, yeah. No, yours wasn't?
No, I think we applied a lot more force.
All right. So that's a great point. So maybe your results don't match up. So let's think why that might happen. So you're saying I might have pulled the car back too far. Okay. So ideally, we want to make sure we're pulling it back the same distance each time. Okay. So for most of you guys, I had you pulling it to that stopper and then you launch from there. Right. So if I change the amount of force, that's going to ultimately change the initial acceleration, right? So greater force, it's going to accelerate faster. So friction should still have an impact on it, though. Should still slow it down a little bit. Okay? So that's right. So that might be one area. Anybody else experience any issues? Data didn't match up as it should have? Did you notice how it was kind of hard, especially with the sliding car, for it to stay on the track? And sometimes when you launched it, it didn't even make it through that second photo gate. So when that happens, that's because the friction is so great, it's going to slow it down before it even reached that 45 centimeter distance that we had originally thought about. So, but hopefully you guys enjoyed that. The questions, if you have a few questions, please make sure that you get these last ones done and turned in so then I can update your grade. Okay, so if you have a couple more, don't forget, finish those last few. It doesn't have to be like long, eloquent, worded sentences from English class. If you want to bullet point it, that is totally fine. So that was from Monday, and for our B kids, it was yesterday, Tuesday. All right, so we got lab from yesterday done. Check. So I said the last thing we got to learn is the Newton's third law. And you guys have heard it before, right? We talked about it at the beginning of the unit. We haven't really talked about, well, what's the overall impact on its motion? So remember, the biggest thing that we've been talking about is even with all of our math, even with all the calculations and stuff like that, that is going to have an impact on the observable motion, okay? It's going to explain why we see things happening in daily life. Why is the semi taking such a long time to speed up on the freeway? Right? Maybe if I remember that every single time I'm behind a semi, I won't honk my horn at them like, come on, go faster, right? Might still happen though, okay? So when we're looking at motion, we want to try to explain and apply these concepts and say, well, what would the impact on the motion be? Or what would I observe out in daily life? Because that's going to be the application. That's going to be the important part, Okay? So Newton's third law, what's it say? For every action, there is a equal and opposite. That's the key. So it's equal and opposite reaction. Okay? So what does that mean then? My example at the beginning of this unit was that obnoxious friend that always high fives you super hard, and you're like, seriously, dude? Like, my hand is burning, it's dying, right? Our example was my hand hits yours, and your hand hits back, right? So that was our initial example. But there's a couple things that I want you guys to remember when it comes to forces. So we know a force could cause motion. I'm pushing on this desk, though, and it's not moving. Does a force always cause motion? No. Remember, we talked about it. You can still have motion and not have unbalanced forces acting on an object. You can have balanced forces where the object's at rest or where the object is moving at a constant speed. So we know that our forces could be a push or pull. We had our 6 different types. We had tension, we had air resistance, friction, gravity, normal, who am I missing? Applied. Okay? The forces that I specifically can do is I can push, I can pull, and that might affect the motion of the object. Okay? Again, if I want to change the motion of the object, I need a unbalanced force. Now, I don't know about you, but no matter how hard I push on the wall, I'm never going to successfully move that wall, right? Because I cannot exert a great enough force. Okay? So when we're looking at those forces and I say, okay, well, I'm leaning on the wall, so I'm pushing on it, right? So your objects, there's always 2 objects. There's me and there's the wall, right? So I push on the wall, and then what's the reaction? The wall pushes back on me, right? Have you guys seen all those Snapchat and TikToks and all that where the student goes running down the hallway and jumps into the lockers? Yeah, we've all seen it. And you're like, really? Why? When is that ever a good idea? I don't know. It would hurt, right? So as they jump into lockers, their body, so they exert a force on the lockers, and then the lockers exert a force on them, right? So if I'm jumping into the lockers because I decided, I'm going to be a TikToker, make money that way, be super cool, be funny, probably wouldn't be. I hit the wall with 50 newtons. How much does the wall hit back with me? 50 newtons, okay? Who's going to move, though? Me or the wall? Me, because I have more or less inertia? Less. So even though we hit each other with the same amount, I might actually need to use like 20,000 newtons to move the wall. So the wall's definitely not going to move. But me, I'm going to end up bouncing back off that wall because that's going to exert enough force on my body to cause my body to accelerate, right? So we know the law says for every action, there's an equal and opposite reaction. I will tell you the one thing that students are going to get tripped up on is I'm going to ask you a question. Like, I hit a baseball with a baseball bat. The bat hits the ball. That's the action. What's the reaction? The ball hits the bat. So my objects are the same. Bat hits the ball, and then the reaction is the ball hits the bat. And then I'm going to ask you, well, which force is greater? And some of you guys are going to tell me that the force of the bat on the ball is greater than the force of the ball on the bat. Is it, though? Good. Why is it not? Newton's third law, every action and reaction are equal, but opposite, different directions, right? Now, the observed motion, what I see, is the bat going to go flying or is the ball going to go flying? The ball is going to go flying because it has less mass, hence less inertia, hence less force required to cause it to accelerate or move, right? Yes. Okay? So that's the hardest part, and that's the part that I'm going to see somebody make a mistake on. they'll be able to repeat it back to me verbatim and say, okay, well, for every action, there's an equal and opposite reaction. They'll get that. They got that. But when I ask them, though, which force is greater, me pushing on the wall or the wall pushing on me, they're going to pick something other than saying they're equal. Okay? Same deal with that baseball that I had talked about. Okay? No matter what, it's going to be equal. Now, the resulting change in the motion might be different. And that resulting change is going to be different because they have different masses. Now, if they have the same mass, the resultant motion will still be the same. Okay? So you got to be careful with that. All right, so we got baseball bat, we got the ball. Okay, so our interacting force pair. When you write out the reaction and the action, so the action, reaction, the two objects are the same. So if you look, bat applies a force to the ball. Let's say that's to the right. Okay? The ball then applies an equal and opposite force to the bat. So that would be then to the left. Okay? So we said it's going to go flying because the baseball has less mass, hence less inertia. Okay? So even though the forces are equal, the resultant observable motion is going to be different. Okay? All right. Car hits mailbox. My action is the car hits the mailbox. What's the reaction? Perfect. Mailbox hits the car. Mailbox goes flying because it has less mass, hence less inertia, therefore meaning it requires a less force to accelerate it. Okay? So as long as you are exerting and hitting that force necessary in order to cause it to accelerate, the object is going to move, right? Now, if that same car runs into like a tree, tree's not going to go flying, right? Because it's not great enough force for that tree to actually move. Okay? So you just got to be careful on that part. That's the one thing that I tend to see. Okay? Last part I want to point out to you guys. This is what you guys are going to be working on for today. Okay? And you will have plenty of time to get it done and shoot it, turn it on in. Okay? So each one of these gives you an example. Remember, the objects stay the same. The direction, though, is going to be opposite. So, for example, in the first one, the baseball pushes the bat to the left. So then I just need to flip-flop the objects. The bat's going to push the ball to the right. So our direction is going to flip-flop. And then I also change the positioning of the objects. So take a look at our next one. The baseball pushes the glove to the left. So I have baseball and I have glove as my two objects being part of this interacting force pair. So my reaction is the glove pushes the baseball to the what direction? Right. And it's going to be to the right because it's going to be opposite. Okay? So these ones go really, really fast for you. I will tell you, if you look down here, you got to be careful with the foot and the ball. So the A is going to kick the ball. C will also kick the ball. So when you're looking at the action-reaction pairs, we're going to have foot A and the ball. And then we'll have foot C and the ball. Okay? So you're going to be doing the interaction, action, reaction pair for both of those. When you go to the next page, this one has so many action-reaction pairs. There's way more than just 6. Okay? Now, question. When you're answering these, the tractor is pulling what to the left? The what? Sorry, I missed it. What's the tractor actually touching and pulling? The rope. Good. And then the rope's going to pull it to the right. The rope here is going to pull the boy to the left, and the boy is going to pull the rope to the right. So just make sure you're considering all of your action-reaction pairs. Okay. I could even look at, okay, well, The ground, how is the ground being pushed? Am I pushing the ground forward, backwards? Okay, and then what's the impact on the actual tractor? So a lot of different options here. And then just a couple of clarifying questions at the very end for you guys to try. Okay? If you would like to work with a friend, you definitely can. Again, this part's going to go really, really fast for you. They don't take very long. And then you do have a concept check. And the reason why I wanted to do the concept check, did I make that right? Concept. Is because it has some of those multiple choice type questions you will see on Monday. Okay, so I wanted to make sure you at least saw a couple multiple choice type questions that you might see on your actual test. Okay, don't forget test A-dayers is on Monday, and then Tuesday will be for our B-dayers. Wednesday, nobody's here. Thursday, B is back. Friday, everybody's off. Okay, so we're wrapping up the 9 weeks pretty fast. If you have anything you still need to turn in, you gotta get it to me ASAP. Okay. All right, guys, you are good to go. If you want to grab a friend, work with somebody else, that is fine. You can talk to them. If you want to pop in headphones.